You ever held two shiny quarters in your hand that look exactly the same? They have the same eagle, the same profile of George Washington, the same words stamped on them, but what if one felt just a tiny bit heavier than the other? You might think something strange is going on, but this very idea is a fantastic way to start thinking about something fundamental to our universe: isotopes. This little mystery of weight is happening all around us, in everything we see and touch, from the air we breathe, the ground beneath our feet. Imagine the entire universe is built from an incredible set of building blocks, far too small for us to see with our eyes alone. These blocks are called atoms. Every single thing you can imagine, a banana, a spaceship is made of these atoms. They are the A, B, C's of physical existence. Understanding how these atoms can be both the same and different at the same time is the key to unlocking powerful tools and deep secrets. It's like knowing the secret recipe for how everything is put together, from the smallest pebble, the most distant star. Think about snowflakes, no two alike, yet all frozen water. Or members of a family. Shared name, shared features, unique characteristics. By asking, why does this feel different even though it looks the same? We take the first step toward nuclear power carbon dating ancient artifacts, diagnosing diseases within the human body. That simple curiosity is the engine of science. Keep the image of the two quarters in mind. One standard, one a little heavier. They have the same value, but one has a little something extra. That extra doesn't change what they are, but it changes a fundamental property. We're diving into the atomic world where the same principle applies. A journey into the heart of matter. Consider this your invitation to the amazing world of atoms. Alright, let's zoom in. Way in. Everything physical is made of atoms, and an atom itself is made of even smaller parts. At the very center of every atom is a tiny, dense core called the nucleus. Think of it as the atom's heart. Inside this nucleus, you'll find two types of particles snuggled together: protons, neutrons. Now here is the crucial part. The number of protons defines the atom. It gives the atom its identity, its name. For example, any atom with exactly 6 protons is always a carbon atom. No exceptions. It's like a rule of the universe. But what about those other particles? The neutrons? Well, they are the something extra we talked about. While an atom must have a specific number of protons, the number of neutrons can vary. This is where isotopes are born. Isotopes are members of the same atomic family. Same protons, different neutrons. Because neutrons have mass, adding or subtracting them changes the atom's total weight. So, you can have a lighter carbon atom and a heavier carbon atom. Carbon-12, 6 protons, 6 neutrons. Stable carbon-13, 6 protons, 7 neutrons. Stable carbon-14, 6 protons, 8 neutrons. Unstable, but they both have 6 protons, so they're still carbon. It's that simple. Let's use an analogy. Imagine you have a collection of toy cars. All the cars painted red belong to the red car family. The red paint is like the number of protons. It defines the family. Some red cars might have 2 seats, others have 4 seats. The number of seats is like the number of neutrons. They're still red cars, but different configurations and different weights. Isotopes are just like that. Same family name, protons. Different weights, neutrons. Now this difference in weight has a huge consequence. The balance between protons and neutrons determines whether an atom is stable, unstable. A stable isotope is like a perfectly built tower of blocks. It can stay that way for, well, pretty much forever. But an unstable isotope is like a wobbly tower. It has a bit too much energy and wants to settle down. It releases that extra energy in the form of particles waves. This process is called radioactive decay, and it's where we get the term radioactivity. These unstable isotopes are the super useful ones we'll talk about next. So we have these unstable isotopes that release energy. That might sound a little scary, but scientists have learned how to use this property in incredibly helpful ways. Think of it like harnessing the power of a waterfall. In medicine, this is a game changer. Doctors can use specific, short-lived radioactive isotopes as tracers. For a procedure like a PET scan, a patient is given a tiny, safe amount of a substance containing an unstable isotope. This substance travels through the body, and because it releases energy, special cameras can track exactly where it goes. This allows doctors to see how organs are functioning, or to pinpoint the location of diseases like cancer with amazing precision. But the usefulness of isotopes doesn't stop at the hospital door. They are also like time machines for archaeologists and geologists. You have probably heard of carbon dating. This technique relies on an unstable isotope called carbon-14. All living things, from trees to people, absorb carbon from the environment, including a tiny predictable amount of carbon-14. When the organism dies, it stops taking in new carbon, and the carbon-14 it already has begins to decay at a very slow, very steady rate. By measuring how much carbon-14 is left in an ancient piece of wood or a fossilized bone, scientists can calculate how long ago it died. It's how we know the age of prehistoric artifacts. And protecting our future. In the world of energy, certain heavy isotopes, like those of uranium, are at the heart of nuclear power plants. When the nucleus of one of these atoms is split, it releases a tremendous amount of energy, which is used to boil water, create steam, and turn turbines to generate electricity for our homes and cities. On a smaller scale, isotopes are industrial detectives. If an engineer suspects a leak in a long underground pipe, they can introduce a small amount of a harmless, radioactive isotope into the fluid, and then use a detector on the surface to find exactly where the radiation is escaping. Even in our environment, isotopes serve as powerful trackers. Scientists can analyze the isotopic signature, the specific ratio of different isotopes, of pollutants in a river or in the air. This signature can act like a fingerprint, allowing them to trace the pollution back to its source, whether it's a specific factory or a natural geological process. From healing the sick and uncovering ancient history to powering our cities and protecting our planet, these tiny atomic variations have a massive and overwhelmingly positive impact on our daily lives. They are the invisible tools that make so much of modern science possible. Section 4. Seeing is believing. How to visualize an isotope. Science is all about making the invisible visible, and that's especially true for something as small as an atom. Since we can't just look at an isotope, we have to build models to help our brains understand them. One of the simplest and best ways is to use physical objects. Imagine you have two colors of marbles, blue for protons and green for neutrons. To build a model of carbon-12, you would take 6 blue marbles and 6 green marbles and clump them together. That's your nucleus. Section 5. Your turn to explore. 3 simple steps to science. Feeling curious? That's fantastic. You don't need a high-tech laboratory to learn more about isotopes. You can take your understanding to the next level with a few easy steps. First, go on a little digital treasure hunt. Find a short, animated video from a trusted source, like a museum, university, a science educator's channel. Visuals are key. Seeing atoms bump around and change in an animation can make the whole process click in your mind. Look for content designed for beginners that uses clear, simple language and avoids heavy details. A good 5-minute video can be more helpful than an hour of reading a dense textbook. Second, get your hands busy. The best way to understand how something is built is to build it yourself. You don't need a fancy chemistry set. Use everyday objects. Grab different colored candies, grab beads, grab Lego bricks, grab little balls of modeling clay. Assign one color to be protons and another to be neutrons. Try building carbon-12. Try building carbon-14. Count out the protons first, then add the extra neutrons. This hands-on activity turns an abstract concept into a physical, memorable experience. It's play, but it's also powerful learning. Third, connect the science to a story. Pick one use and dive into its story. Read about carbon dating and the Dead Sea Scrolls. Watch a clip about medical isotopes helping a patient. When you connect the science to a human story, a mystery solved, a life saved, it becomes easier to remember. Next time, half-life, the simple clock inside atoms. See why isotopes fade, how carbon dating keeps time, what it means for medicine, what it means for our planet. Bring your candies. Lego will make decay visible. If this helped, tap subscribe and the bell so you don't miss it. Share your builds or isotope stories in the comments. Keep exploring. See you in the next chapter.